Okay. So, this equation we have seen, this is equation 8. Now, another thing is that it is assumed that change in load is sensitive to the speed or frequency variation. We are assuming the load is frequency sensitive, it is not insensitive to the frequency, we are assuming that load is frequency sensitive, right. However, for small changes in system frequency delta f, because the delta f change will be very small, right, the rate of change of load with respect to frequency, that is your del P L upon delta f, can be regarded as constant, right. That means delta P L delta P f will regarded as it can be regarded as a constant, although but we are assuming that load is sensitive to the change in frequency. Therefore, this load changes can be expressed as your delta P L upon delta f into delta f. This we are taking as a constant, and we are assuming that because this is due to the your very small change in delta f, this is very small into delta f, and this we define actually d into delta f. This is equation 9. If you do not consider that, d is equal to 0, later we will see, but we will assume that load is sensitive to the change in frequency. So, in that case delta P L upon delta P f can be regarded as a constant, right, and how we will take that later will come, later we will take numerical small example will come, right. So, this is your d into delta f. Therefore, the power balance equation, this one delta P g minus delta, it has two terms, one is the rate of change of kinetic energy, that is 2h, you know, rate of change of kinetic energy means your what you call the power. So, 2h P r upon f 0 d dt upon delta f plus that d into delta f term, the previous equation, that means this term, right. So, look, we will take Laplace transform on both sides later, but except using s in that your associated with time constant, nowhere I will put delta P g s or delta P L s or your delta f s, it is understandable to you. So, if we put everywhere s, it will be little bit clumsy. So, I do not want that. Now, what you do, this equation both side you divide by P r, right, both side P r. So, this is delta P g upon r minus delta P L upon r, this P r you divide, it is gone. So, it is 2h upon f 0 d dt upon delta f plus d upon P r into delta f. So, if you assume this is a base value, then delta P g upon it is megawatt, of course, delta P g upon delta it is in per unit minus delta P L it is also per unit, then 2h upon f 0 d dt upon this delta f is in hertz, right. This delta f, remember hertz, f 0 is hertz, h in second, here no unit change, it is in hertz, and d will be your what you call in per unit, because this d is equal to your delta P L upon delta f, and you are dividing it by P r. So, delta P r will be delta P L upon your P r, delta P L upon delta f, right, into 1 upon P r. So, delta P L upon this P L, delta P L P r, it will become per unit. That is why this and this, but this will remain hertz, frequency will be hertz, right. That means unit of d will be per unit megawatt per hertz. So, that is why this d here is written in per unit. So, d is also per unit into delta f, this is written, right. This is equation 10. So, next is your that means your next one, just hold on. Therefore, if you take the Laplace transform both this after this delta P g, delta P L, d all is in per unit. So, again and again this per unit will not be returnable, but equation 10 onwards all these values unless and until I mention all are in per unit only, right. But again and again I will not write per unit, then things will become clumsy. I do not want that, but take equation 10 onwards everything is in per unit, and frequency of course is in hertz, h will remain second, f 0 also will remain in hertz, right. But this delta P g value, delta P L value, d all are in per unit, right. So, again and again I will not write, but understandable. So, if you and every time I will not put delta P g s, delta P L s or delta f s, right, because it is Laplace transform understandable, such that mathematics writing will be easier, right. So, but it is understandable. So, you take the Laplace transform of this equation both sides, you take the Laplace transform, if you and simplify, you take the Laplace transform and then you simplify. If you do so, then you will get delta f is equal to delta P g minus delta P L upon d plus 2h upon f 0 into s, this you know now, right. So, because if you take that this equation this is a Laplace transform, it will be S into initial conditions are 0 you assume, right, S into your delta Fs, but the S I am in bracket your what you call not considering, then again and again for all the variables I have to put. So, we do not want that, right. So, it is your 2h upon F0 S into delta your F, and this will be d into this thing, all these things you take the Laplace transform and simplify, right. So, if you do so, it will become del F will become delta Pg minus delta PL divided by d plus 2h upon F0 into S. This way it will come, or you can what you can do is this one you further simplify, that means this how this thing is coming, that delta F is equal to delta Pg minus delta PL into Kp upon 1 plus STP. How things are coming from this equation, numerator and denominator you divide it by d, right. If you I mean let me write for you, this is actually the equation, delta F is equal to delta Pg minus delta PL divided by d plus 2h upon F0s. This is the equation. Numerator and denominator you divide by d, then delta F will be is equal to delta Pg minus delta PL into 1 by d, right, divided by d divide it will be 1 plus 2h divided by your df0 into s, right. You define Kp is equal to 1 upon d and Tp you call Tp is the power system time constant, it is 2h upon df0, this will be in second, right. So, if you define this, then this equation will become Kp upon 1 plus STP into delta Pg minus delta PL. Just hold on, this is your Kp upon 1 plus STP into delta Pg minus delta PL, right. So, same thing, just I have written left hand side, here it is written right hand side. So, this delta F is equal to delta Pg minus delta PL into Kp upon 1 plus STP. This is equation 11. So, where Tp is equal to your power system time constant 2h upon df0 and Kp is equal to 1 upon d is equal to we call sometimes gain of power system. So, with this governor transfer function we got, turbine we got, and this generator we got, right. This is actually sometimes we call this is power system transfer function or generator transfer function, right. Once you get it, then you combine governor, turbine and generator, because here we have also related everything, delta Pg we have related to delta F, of course, delta PL is there, right. So, this one if you represent in a small block diagram, so this is delta Pg and this is delta PL, delta PL is minus sign, delta Pg plus, because delta Pg minus into this one, then in block diagram Kp upon 1 plus STP, that is delta F, small delta F, capital they are same, I have written here, right. This is the block diagram represent our generator load model. Sometimes we call this part we call sometimes power system model also, right. So, this part, so delta Pg we have related with the turbine, your what you call turbine power output, right, delta Pg, then that one also related to delta E governor output, and then finally delta F was the input and U, right. So, all these things we have made it. Now, if you combine, now it will be like this, because this block this governor one we got it, no, U minus del F R upon this one, this is delta E. Let me just 1 minute, just you go now one after another, right. Then just see this part, this is the governor part, this we have made it, just hold on, I will show you, just hold on. This is your speed regulation parameter R, just hold on, this such that you will have a good feeling about this, that how we actually develop the model, right. Just hold on, if I can make it once again here, right. So, this is your turbine part, first let me show you, this is your turbine part, this is your turbine part 1 plus SKR upon 1 plus STT into 1 plus STR, delta Pg and delta E is the input, delta Pg is the output. So, this is delta Pg is the output, delta E is the input, and this term is added here, right. So, these two terms are there. So, we have broken it, right, because of the state variable form. So, this is actually in between one variable is added delta p v, right, but this is the 2 and delta, and this one just now we have made it no delta f small or capital does not matter, delta p g minus delta p l into this one just now we have made it, and this one already we have made it no delta e into u minus 1 upon r 1 upon 1 plus s t g, and this is input was delta f also in that block diagram it was shown you, right. All these things you just make it and just add it no, it is completing a closed loop frequency or closed loop your what you call transfer function. So, just 1 minute, if I get it immediately I will show you, just 1 minute, if it is here or not, just 1 minute. If I get it I will show you. This is your turbine model, this is just hold on, if I get it I will show you again, just hold on. Here this speed this one we took that speed changer was not shown here, speed changer was not shown here, but somewhere I made a speed changer also, and this one is the final block diagram, somehow it has been missed somewhere here, right. But this already we have derived u minus, I derived for you also here, I derived for you this one I have derived for you, delta is equal to u minus delta f, it is in front of me actually, right, into 1 upon this one also derived, this one also derived. So, this was also clubbed together and its input was delta f no, in input was delta f. So, this delta f is equal to same thing small delta f, right. So, this is your this is delta f same thing. So, this is coming here, this delta f actually coming from here. So, this is a closed loop system. So, with this is the block diagram representation of a generating unit with a reheat turbine, it is isolated or single area power system, what is area will come later. So, this is actually your what you call that isolated power system, this is governor, this is turbine and this is your power system. So, this is actually I have written rotor inertia load, right, this dash portion is turbine and this portion is governor and this is u is your control signal actually. So, now what we will do this with this one we have got this block diagram. Now, what we will do is that we have to your what you call we have to go for state space representation and then we will see the steady state error and other things. So, what you do this we have to make it in the form of x dot is equal to a x plus b u, right, that way you have to make it. So, this one we have taken as this output is taken as x 1, right, this delta p g is taken as x 2, in between because we have to make it a state variable, this one output of this one we have taken as x 3 and this one output of this governor time constant this is x 4, right, and this is u this thing. So, we have to write down and assuming that all the initial conditions are 0. So, we have to write down x 1 dot, x 2 dot, x 3 dot and x 4 dot and we have to put it in the state variable form, right. So, what we will do is that in the state space representation this all these things are shown here, delta f is taken as x 1, delta p g taken as x 2, this I have given a name delta p v is x 3 and delta e as x 4, these 4 state variables, right. So, all these things are given here, delta f x 1, delta p g is actually x 2, delta p v x 3 and delta e x 4. So, differential equation are written by your describing each individual block of figure 12, this is figure 12, this is figure 12, right. In terms of state variable, note that S is replaced by d dt because it is in a Laplace transform. So, what you will do that you write all the equations x 1 dot, x 2 dot, all I have written here x 1 dot, x 2 dot, x 3 dot, x 4 dot, but that is I have written here, but I am writing here for you, right, such that things will be understandable. So, just see how we are writing. First you write down the equation for your x 1. This is your x 1, right. So, how we will do this? Just 1 minute here, one or two small thing you have to your what you call you have to understand, right. First you see this x 1, this x 1. So, x 1 is equal to, I will write little bit slowly such that handwriting will be better, right, because this is a pen and paper. So, this is your x 1 is equal to this delta p g actually your x 2. So, basically it will be x 2 minus say delta p l, because delta p g you have taken x 2, that is your x 2 minus delta PL, right, into Kp upon 1 plus STP, right. So, that is your x1. You cross multiply, that means it will be x1 then Sx1 Tp, we are taking S and x1 together, is equal to Kp x2 minus Kp into delta PL, right. That means this Sx1, actually S is d dt, so Sx1 will be x1 dot, therefore, because S actually is d dt, therefore, it will be x1 dot, that means your x1 dot into Tp is equal to Kp x2 minus Kp into delta PL, right. That means, just hold on, that means this x1 dot Tp is equal to minus x1 plus Kp x2 minus Kp into delta PL. Therefore, x1 dot is equal to minus 1 upon Tp x1 plus Kp upon Tp x2 minus Kp upon Tp delta PL. So, this is actually, this is what I have written here, this equation. This is equation 12, minus 1 upon Tp x1 plus Kp upon Tp x2 minus Kp upon Tp delta PL. This is equation 12. So, this is what I have written here. This is actually your equation 12. So, this I have written here directly instead of writing so many steps, but here I showed you what is x1 dot is equal to, right. Next, we will write your other equations. Now, before writing x2 dot, I will write x3 dot for you. Why? Now, we will know, right. First, I will write x3 dot. So, you come to the your diagram, this x3, first I will write x3 dot and then I will come to x2 dot. So, if you look at the diagram, that x3 will be equal to x4 into 1 upon 1 plus STT. So, from this diagram only, x3 is equal to x4 divided by 1 plus STT. Then go for cross multiplication again, it will be x3 plus your Sx3 into Tt is equal to x4, right. That means your Sx3 is x3 dot. So, it is x3 plus x3 dot Tt is equal to x4. That means your x3 dot Tt is equal to your minus x3 plus x4. That means your x3 dot is equal to minus 1 upon Tt x3 plus 1 upon Tt x4. So, that means this equation, this equation x3, it is x3 dot is equal to minus 1 upon Tt x3 plus 1 upon Tt x4. This one we write next, right. Why I wrote this one first, you will know now. This is actually equation 14. This is your equation x3 dot. Now, we will come to x2, because in the x2 dot equation this x3 dot is required, that is why x3 dot is obtained first, right. Next, you come to your x2 dot, right, this x2 dot. So, this x2 is equal to x3 into whole of this thing. Therefore, your x2 is equal to, this is x2, this is x2 is equal to 1 plus SKR TR divided by 1 plus STR into your this x3, right. Now, when you now multiply with this one, cross multiplication. So, 1 plus STR x2 is equal to, multiply this one, it will be x3 plus Sx3, because S is here, into Kr into Tr, right. So, if you multiply this one, then it will be x2 plus Sx2 Tr is equal to x3, it is Sx3 means x3 dot Kr TR, because x3 dot is coming, because x3 dot you have to substitute from that equation. This x3 dot you have to, this x3 dot value you have to substitute here, otherwise you cannot. That is why I wrote that equation 3 first, right. So, the way I have chosen the state variable. So, this one actually Sx2 is x2 dot. So, it is x2 plus x2 dot into Tr is equal to x3 plus Kr into Tr, and this x3 dot, this one minus 1 upon Tt x3 plus 1 upon Tt x4, you substitute, it will minus 1 upon Tt x3 plus 1 upon Tt x4 you substitute, right. That means my x2 dot Tr is equal to minus x2, right, plus x3 plus you multiply, sorry, it will be minus Kr Tr upon Tt x3, right, then it is plus Kr Tr upon Tt x4, right. Just hold on, I have to go little bit up, otherwise you cannot see this, right, this one, right. Then both side you divide by Tr and simplify, then you will get this equation, then you will get equation 13, then you will get equation 13, right. You both side you divide by Tr and simplify, then you will get your x2 dot is equal to minus 1 upon Tr x2 plus 1 upon Tr minus Kr upon Tt x3 plus Kr upon Tt x4. This is equation 13, right. So, x1 dot, x3 dot, x2 dot, all I showed just to make it, right, just to save some time I did not do further, but you make this thing. Next your x4 dot, right, just see the x4 dot. Now, for x4 look at this diagram, right, this is your x4, this is your x4. So, you can write x4 is equal to this is u, and this delta f means x1, this means x1. So, it is plus u minus x1 in by r, right. So, it will be u minus x1 by r, right, into 1 by 1 plus s t g, right, that is x4 is equal to, right. So, make cross multiplication again. So, writing directly it is x4 and s x4 t g, s x4 means x4 dot. So, it is x4 dot, then t g is equal to this term writing first minus x1 upon r plus u, or x4 dot t g is equal to this one writing first minus x1 r, right, minus x4 plus u, right, or x4 dot is equal to minus x1 upon r t g minus 1 upon t g x4 plus 1 upon t g u, right. This is actually your equation number 15, this is equation 15, that is x4 dot minus 1 upon r t g x1 minus 1 upon t g x4 plus 1 upon t g u, this is equation 15. I think up to this it is your what you call, it is understandable that how to obtain all state variable equation x1 dot, x2 dot, x3 dot, there are 4 state variables, right, right. So, I have taken state variable like this, your what you call here x1, x2, x3, x4. If you can take this is x1, x2, x3, x4 also no problem, the way you want you can take this way, right. So, this is all this thing. After that we have to put this equation in x dot is equal to ax plus bu form, right. That means this equation we have to write that you are in this form x dot is equal to ax plus bu plus gamma p, this gamma p form, this way you have to write this equation. Now, if you do so, then what you will get, right. So, when you make it x dot is equal to x plus bu plus gamma p, right. So, this is actually your this one your A matrix, right, and bu, this is u, this is u, this is actually this one will be b, and this is delta pl. Gamma p means it is your what you call gamma p means this p actually is equal to your pl, right. I made delta pl because change in the load. So, delta pl. So, u and delta pl, but if you look at this equation, just hold on, just hold on. This is also we have taken delta PL. So, this is I have also written delta PL. So, P is equal to actually delta PL, right. So, if you put in this form x dot is equal to x plus bu plus gamma p, just hold on, right, just hold on. So, this A is actually state transition matrix, right. B is equal to your control transition matrix and gamma is equal to disturbance transition matrix. This is actually this one actually is your gamma, right. This is actually is your gamma, this is gamma and this is B, this is A, B and gamma, right, and x1, x2, x3, x4 are the state variables, u is the control variable and delta PL basically is the disturbance in the system, right. So, this way if you write, then if you look at this those equations, that equation 12, 13, 14 and 16, this x1 dot is equal to actually minus 1 upon Tp x1. So, minus 1 upon Tp x1 plus Kp upon Tp x2 plus Kp upon Tp x2, right. No x3, x4 term is involved in this equation. So, their coefficients are 0. So, it is 0, 0, right, because x1, x2, x3, x4, no u term is available involved in this equation. Therefore, all this is 0, right, and then disturbance term is there minus Kp upon delta PL. So, in the very first row this is minus Kp upon Tp into delta PL is here. This is x1 dot is written, I think you know this. Similarly, x2 dot is equal to your x1 is not involved here. So, it is 0, right. Then this one your x2 dot, that is minus 1 upon Tr. So, minus 1 upon Tr is here, right. Then this one 1 upon Tr minus Kr upon Tt x3. So, 1 upon Tr minus Kr upon Tt x3 the third term and fourth term Kr upon Tt x4. So, Kr upon Tt, this is x4, right, and there is no u term, no disturbance term. So, corresponding this is 0, this is 0, right. Now, third term only minus x3 and x4 are involved, others everything is 0. So, x1 is 0, x2 is 0, it is minus 1 upon Tt and it 1 upon Tt, this is x3, this is 0, this is 0, right. And last term x4, x1 and x4 is involved, x2, x3 is not there, both are minus sign. So, minus 1 upon Rtg 0, 0 and x4 is this minus 1 upon Tg, this one x4, and it is u 1 upon Tgu. So, 1 upon Tg is here because this is u, but here it is 0, right. So, this is actually written in this form x dot, that is x dot is equal to actually x1 dot, x2 dot, x3 dot, x4 dot, capital X dot anyway is equal to a into x plus b into u plus gamma into p. This way we have written this equation. So, it can be written as x dot is equal to x plus bu plus gamma p, where x transpose I have taken state variable x1, x2, x3, x4, A matrix is this matrix is A matrix, right, and it is B matrix 0, 0, 0, 1 Tg, but I have written B transpose, dash is transpose as the space can be accommodated. So, 0, 0, 0, 1 upon this is B transpose, that is why it is written that this is A actually, and similarly that gamma actually minus Kp upon Tp 0, 0, 0, but taken as a transpose as that space can be saved here. So, gamma dash is equal to minus Kp upon Tp 0, 0, 0, and this P is the disturbance, that is your delta PL, right. I hope you have understood this state variable. Thank you very much. We will be back.